All right, so here is our objective, and this is topic 1.6. All right, here's the machine that collects this data. You know, this huge, complicated machine that spits out these graphs. This comes from England, and this is where you don't see it back here, but this is like with the computer piece back here that spits out this data. All right, I think the computer is like right there. You can see it right there. All right. And it's calculating the binding energy by shooting X-rays at a sample and ejecting electrons. All right, that's what we're going for. All right, now there's two main principles that allow you to be able to read these and predict them. The one thing is the off-bond principle, and that electrons go to the lowest energy orbital first, and they fill it in patterns, and that's the same for every atom. Okay, so I want you to get down this piece that the electrons fill orbitals in patterns. The next piece that's important, now we've got three different elements here, and hydrogen, this is nitrogen, and this is aluminum, is that any differences in the graphs you can explain by nuclear charge and distance to the uh, nucleus for the electrons. Not necessarily the radius, but the distance the electrons are. And I'll go over an example. All right. So predicting, let's say this is our electron configuration, 1s2, 2s2. What is that on the periodic table? That is going to be right here, in here. 1s2, it's oxygen. All right. What is it going to look like? Well, I'm going to have my 1s2 peak 1. Then I'm going to have my 2s2. And then I'm going to have my 2p4. And this peak would be like halved. Okay. Now, for helium, here's helium. What's its PES data going to look like? Well, we know its configuration. It's got 2 electrons. So it's going to simply have a 1s2 peak, just like that. All right. Now, how about this one? Well, we already did that one. This is interesting. Let's do it for fluorine. This should be 2p5. Okay. What's that one going to look like? Well, it's going to have a 1s2, 2s2, and then a 2p5. Well, this is going to be 5. Okay. And that's 5. Because we already did, and this is fluorine right there. This is different than the one I just did 2 previous slides. All right, what's hydrogen going to look like? Well, hydrogen, it's got a 1s1, so it's just going to have that one peak right there. All right, that one peak. How about this one? This is nitrogen because of the 7. Nitrogen has 7 electrons. It's going to have how many different peaks? 3. These two are going to be the same height, and that one's going to be a little bit bigger. All right. What element is this? All right, well, how many peaks do we have? 1, 2, 3, 4, 5. We have 5 peaks. This is the 1s, 2s, 2p. All right. What is this? This is, I believe, silicon. Oh. Okay, I was wrong. I looked at my periodic table down here, and it's not silicon, it's phosphorus. All right, because phosphorus ends in a 3p3. It's got a total of 15 electrons, atomic number of 15. That's phosphorus, not uh, silicon. Silicon would have one less, right? Now, to account for differences in these diagrams, here is aluminum, these 3 elements, all right? Aluminum, hydrogen, nitrogen. Oh. And you go by you'll notice that this 1s, that's the 1s, that's the 1s, and that's the 1s, okay? But you'll notice it's significantly higher in aluminum and lower in hydrogen. And why is that? Well, you'll remember all differences can be explained with nuclear charge. And in this case, it's nuclear charge. You'll notice that the nuclear charge is going up in three of them, okay, in each one successively. So let's look at it in a little more depth. For hydrogen, here's that peak. All right, it's at 1.31. And for nitrogen, the peak's at 39.6. And for aluminum, it's a 151. Well, the reason is that aluminum has got 13 protons holding those inner electrons of the 1s, and hydrogen only has one. Therefore, it says bidding. It should be binding. It's harder to take electrons from aluminum than it is for the hydrogen. Okay, let me know if that helps and leave some comments and questions. And thanks for listening. Thanks for listening. All right, rock on.